Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How gravity bends light in space. Light travels in straight lines through empty space. Or at least, that's what our everyday experience suggests. A laser beam shoots across a room in a perfectly straight path. Starlight reaches Earth from distant stars without deviating from its course. But this intuition breaks down when gravity becomes involved. In the presence of massive objects, light follows curved paths, bending around stars, galaxies, and even clusters of galaxies in ways that reveal one of the most profound insights about the nature of space, time, and gravity itself. The story begins with Albert Einstein's general theory of relativity, published in 1915, which fundamentally reimagined what gravity is. Newton had described gravity as a force. Masses attract each other across distance through some invisible pull. Einstein proposed something radically different. Gravity, he suggested, is not a force at all, but rather a consequence of the geometry of space-time itself. Massive objects don't pull on other objects. Instead, they warp the fabric of space-time around them, and objects simply follow the straightest possible paths through this curved geometry. Imagine space-time as a stretched rubber sheet. Place a bowling ball on the sheet, and it creates a depression, warping the flat surface into a curved shape. Now roll a marble across the sheet near the bowling ball. The marble's path curves as it moves through the depression, not because the bowling ball is pulling on it, but because the surface itself is curved. The marble is still following the straightest path it can, what mathematicians call a geodesic, but in curved space, straight lines look curved to outside observers. This is what happens with light near massive objects. The light is following a geodesic through space-time, travelling along the straightest possible path. But because space-time itself is curved by the presence of mass, that path appears curved when viewed from our perspective. The light isn't being pulled by gravity in the Newtonian sense. It's simply following the geometry of space-time, which has been warped by mass. The amount of bending depends on two factors: the mass of the object doing the bending and how close the light passes to that mass. More massive objects create deeper curves in space-time, causing more dramatic bending. Light passing closer to a mass experiences stronger curvature than light passing farther away. For most objects we encounter in daily life, this bending is utterly negligible, far too small to detect. Even for something as massive as Earth, the bending of light is minuscule. A beam of light grazing Earth's surface would bend by less than 1,000th of a degree. But consider the Sun. With a mass 333,000 times greater than Earth, the Sun creates a significant warp in space-time around it. Light from a distant star passing close to the Sun's surface is deflected by about 1.75 arc seconds, a tiny angle equal to roughly the width of a quarter viewed from 2 miles away, but measurable with careful observations. This prediction of general relativity was first confirmed during a solar eclipse in 1919, when stars near the Sun's position in the sky appeared slightly displaced from their normal locations. The Sun's gravity had bent their light as it passed by, making the stars appear to be in slightly different positions than they actually were. This gravitational bending of light becomes dramatically more pronounced around more massive and compact objects. A neutron star, containing more mass than the Sun, compressed into a sphere only about 12 miles across, creates such severe space-time curvature that light from the far side of the star can bend around it and reach an observer on the opposite side. You could theoretically see more than half of the star's surface at once because light from behind curves around to the front. Black holes represent the extreme limit of gravitational light bending. At the event horizon of a black hole, space-time is curved so severely that light emitted outward from that surface is bent back inward. The escape velocity at the event horizon equals the speed of light, which is another way of saying that space-time curvature there is so extreme that even light following its straightest possible path still curves back toward the black hole. Just outside the event horizon, there's a region called the photon sphere, where light can orbit the black hole in unstable circular paths, bent continuously by the intense curvature of space-time. The shadow of a black hole, the dark region we see in images like the famous Event Horizon Telescope picture of M87's supermassive black hole, exists because of this extreme light bending. Light that passes close enough to the black hole is captured, unable to escape, creating a dark silhouette. The bright ring surrounding this shadow is light from the accretion disk that has been bent and focused by the black hole's gravity, with some photons having orbited partway around the black hole before reaching the observer, creating multiple images overlaid on each other. Gravitational lensing occurs when light from a distant object passes near a massive object on its way to Earth. The massive object acts as a lens, bending the light and focusing it toward Earth, just as a glass lens bends and focuses light. Galaxies and galaxy clusters containing hundreds of billions or even trillions of times the Sun's mass are particularly effective gravitational lenses. When a massive galaxy cluster lies between Earth and a more distant galaxy, the cluster's gravity bends light from the background galaxy, often creating multiple images, arcs, or even complete rings. Einstein predicted a specific case called an Einstein ring, which forms when the lensing mass, the background light source, and the observer are perfectly aligned. In this configuration, the background object's light is bent equally in all directions around the lensing mass, creating a circular ring of light. Perfect Einstein rings are rare because perfect alignment is unlikely, but numerous partial rings and arcs have been observed where the alignment is close but not exact. Strong gravitational lensing creates multiple images of the same background object. Light from the source can take different paths around the lensing mass, arriving at Earth from different directions. An observer sees the same galaxy or quasar in multiple locations in the sky simultaneously, each image distorted differently depending on the path the light took. By analysing these multiple images, their positions, brightness and distortions, astronomers can map out the distribution of mass in the lensing object, including the dark matter that can't be seen directly. One of the most famous examples of gravitational lensing revealed itself in the Hubble Deep Field images. A massive galaxy cluster acts as a natural telescope, magnifying and brightening galaxies far behind it. Some of the most distant galaxies ever observed were discovered this way, their light amplified by gravitational lensing to the point where even these incredibly faint, distant objects become visible. Without the magnification provided by the intervening cluster's gravity, these galaxies would be too faint to detect, even with our most powerful telescopes. Weak gravitational lensing is a more subtle effect. Rather than creating obvious multiple images or dramatic arcs, weak lensing slightly distorts the shapes of background galaxies. Each galaxy is stretched and sheared by a tiny amount, usually only a few percent. Individual distortions are impossible to distinguish from the galaxy's natural shapes, but by measuring the shapes of thousands or millions of galaxies and looking for statistical patterns in their distortions, astronomers can map out the distribution of matter, including dark matter, along the line of sight. This technique has become one of the most powerful tools for studying dark matter distribution in the universe. Gravitational lensing also affects the apparent brightness of objects. When a massive object passes between Earth and a more distant star, the foreground object's gravity can focus the background star's light, temporarily brightening it. This gravitational microlensing is used to detect exoplanets, When a star passes in front of another star, the foreground star's gravity creates a brief brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence even though the planet itself is far too faint to see directly. The time light takes to travel along different paths around a gravitational lens can vary. Light taking a longer path around one side of a lensing galaxy arrives later than light taking a shorter path around the other side. For variable sources like quasars, which change in brightness over time, this time delay becomes observable. A brightening in one image of a lensed quasar will appear days, weeks, or months before the same brightening appears in another image, the delay corresponding to the difference in light travel time along the different paths. Measuring these time delays allows astronomers to determine distances to the lensed objects and constrain cosmological parameters like the universe's expansion rate. Space-time curvature near massive objects doesn't just bend light spatially, it also affects light's frequency through gravitational redshift. Light climbing out of a gravitational well loses energy, shifting to longer wavelengths and lower frequencies. Photons emitted from the surface of a white dwarf, neutron star, or near a black hole arrive at Earth redshifted compared to identical photons emitted far from any massive object. This gravitational redshift is distinct from the Doppler shift, caused by motion. It's a consequence of how time itself runs slower in stronger gravitational fields. The ability of gravity to bend light provides one of the most direct ways to test general relativity. Every observation of gravitational lensing confirms Einstein's predictions about how space-time curvature works. The precise angles at which light bends, the patterns of multiple images, the time delays between images, and the gravitational redshift all match the predictions of general relativity with remarkable accuracy. Alternative theories of gravity make different predictions, and so far, every test has vindicated Einstein's century-old theory. Gravitational lensing has become an essential astronomical tool. It allows us to study the distribution of dark matter by observing how it lenses background galaxies. It magnifies distant galaxies, enabling studies of the early universe that would otherwise be impossible. It reveals exoplanets orbiting distant stars. It measures cosmic distances and the expansion rate of the universe. All of this is possible because massive objects warp spacetime, and light faithfully follows the curves and valleys of that warped geometry. The universe is filled with matter, and that matter curves spacetime everywhere. Light from the most distant galaxies has travelled billions of years to reach Earth, passing countless galaxies, galaxy clusters, and vast expanses of dark matter along the way. Every massive structure the light passes deflects it slightly, creating a cosmic hall of mirrors where every photon's path is bent and redirected many times. The images we see in our telescopes are not straight-line projections from their sources, but rather the accumulated result of countless tiny deflections as light navigates the curved spacetime of our universe. The geometry of the universe itself, on the largest scales, also affects how light travels. If the universe has overall positive curvature, like the surface of a sphere, light paths will eventually converge. If it has negative curvature, like a saddle shape, light paths diverge. Current observations suggest the universe is nearly flat on the largest scales, meaning that, on average, over distances spanning billions of light years, light travels in straight lines. But locally, around every massive object from planets to galaxy superclusters, space-time curves, and light follows those curves, revealing the intimate connection between matter geometry and the paths that light traces through the cosmos. How planets get their beautiful rings. When you think of planetary rings, Saturn immediately comes to mind, with its magnificent system of bright bands encircling the planet like a cosmic halo. But Saturn isn't alone in possessing rings. Jupiter, Uranus, and Neptune all have ring systems of their own. Though far less prominent, even some asteroids have been discovered with tiny rings circling them. These structures, some broad and bright, others narrow and faint, all share a common origin story rooted in gravity, orbital mechanics, and the sometimes violent history of the solar system. The basic ingredients for planetary rings are surprisingly simple. Countless small particles, ranging from dust grains smaller than smoke particles to chunks of rock and ice the size of houses, all orbiting a planet in a flat disk. What makes rings special isn't the individual particles but their collective behaviour, the way millions or billions of objects interact through gravity and collisions to create structures that can span hundreds of thousands of miles yet be only tens of meters thick. Rings form through several different mechanisms, and understanding these processes means understanding both creation and destruction, both gentle accumulation and catastrophic violence. The first and perhaps most dramatic way rings can form is through tidal disruption. Every planet generates a gravitational field that weakens with distance, and this creates tidal forces on any object orbiting nearby. If you imagine a moon orbiting close to a planet, the side of the moon facing the planet experiences stronger gravity than the side facing away. This difference in gravitational pull creates a stretching force that tries to pull the moon apart. There's a critical distance from any planet, called the Roche limit, inside which these tidal forces become stronger than the moon's own gravity holding it together. Cross this threshold, and the moon cannot remain intact. If a moon migrates inward through various processes, or if it formed inside this limit, it will be torn apart by tidal forces. The material doesn't disappear, it spreads out along the moon's orbital path, and over time, through collisions and gravitational interactions, it forms a flat ring around the planet. Picture this process in your mind. A small moon, perhaps captured from elsewhere in the solar system or formed in orbit around the planet, slowly spirals inward. Tidal interactions with the planet transfer energy and angular momentum, gradually changing the moon's orbit. As it crosses the Roche limit, cracks begin to form. Pieces break away, first small fragments, then larger chunks. The moon doesn't explode dramatically. It comes apart more gradually, like pulling apart a piece of bread. Each fragment continues orbiting the planet independently, and as they collide and break into smaller pieces, they spread into a disk of debris. This process may have created some of Saturn's rings, though the origin of Saturn's ring system remains one of the great puzzles in planetary science. The rings are remarkably bright and rich in water ice, suggesting they might be relatively young, perhaps only a few 100 million years old, rather than as ancient as the solar system itself. One theory suggests that a small icy moon, perhaps 200 miles across, wandered too close to Saturn and was torn apart by tidal forces. The shattered remains spread into the magnificent ring system we see today. Another way rings form is through collisions. Imagine two moons orbiting a planet on paths that eventually intersect, or an asteroid from elsewhere in the solar system crashing into a moon. The impact releases tremendous energy, shattering both objects and ejecting debris into space. Some of this material falls back onto the planet or escapes entirely, but much of it remains in orbit, gradually spreading into a ring. This collision scenario might explain some of the fainter, darker ring systems. Jupiter's rings, for instance, are composed of very small dust particles that appear reddish-brown, suggesting they might come from meteorite impacts onto small inner moons. When a meteorite strikes one of these tiny moons, it kicks up dust that then orbits Jupiter. This dust doesn't stay in the ring system forever. It gradually spirals inward due to interactions with Jupiter's magnetic field and atmospheric drag, but it's constantly replenished by new impacts. Rings can also form from a volcanic activity on moons, though this is a less common mechanism. Jupiter's moon, Io, is the most volcanically active body in the solar system, with eruptions constantly spewing material into space. Some of this material, particularly atoms of sodium and sulfur, forms extended clouds around Jupiter. While not a traditional ring of solid particles, these atomic clouds occupy ring-like regions and show that rings can have diverse origins and compositions. The shepherd moon mechanism plays a crucial role in maintaining and shaping rings once they form. Small moons orbiting just inside or outside a ring can gravitationally interact with ring particles, confining them to narrow bands. Imagine a ring particle in an orbit that would normally cause it to drift outward. As it approaches a shepherd moon, orbiting outside the ring, the moon's gravity tugs on it, altering its orbit and deflecting it back toward the ring. Similarly, a shepherd moon orbiting inside the ring can prevent particles from drifting inward. These gravitational interactions can create remarkably sharp ring edges and can even maintain gaps within ring systems. Saturn's moon Prometheus and Pandora act as shepherd moons for the narrow F ring, one of Saturn's outermost rings. The F ring is only a few hundred miles wide, but thousands of miles long, and without these shepherd moons, it would spread out and dissipate over time. The moon's gravity creates a delicate balance, continuously sculpting the ring into its narrow form. Resonances add another layer of complexity to ring formation and structure. When ring particles orbit at certain specific distances from a planet, their orbital period can be a simple fraction of a moon's orbital period, perhaps half as long, or a third or 2/5. At these resonant locations, the gravitational tugs from the moon occur at the same point in each orbit, adding up over time and creating powerful effects. Resonances can clear gaps in rings, sweeping particles out of certain orbital paths, or they can concentrate particles, creating narrow ringlets. The Cassini division, the prominent gap in Saturn's rings, visible even through small telescopes from Earth, exists primarily because of a resonance with the moon Mimas. Particles orbiting in the Cassini division have an orbital period exactly half that of Mimas. The repeated gravitational interactions at this resonance gradually push particles into different orbits, maintaining a gap nearly 3,000 miles wide. The particles within rings are not static, they're constantly colliding with each other, and these collisions shape the ring's structure and evolution. When two chunks of ice collide gently in Saturn's rings, they might stick together, growing larger. But more energetic collisions shatter particles into smaller pieces. There's a balance between these processes, and over time, rings develop a characteristic size distribution of particles, with many small particles and fewer large ones. These collisions also dissipate energy, causing the ring to flatten. Imagine particles orbiting at slightly different inclinations, some tilted a bit relative to others. When they collide, the vertical component of their motion is randomized and gradually damped out through repeated collisions. The result is that rings become extraordinarily thin relative to their width. Saturn's main rings span about 175,000 miles from inner edge to outer edge, yet they're typically only about 30 feet thick, a ratio that's thinner than a sheet of paper if scaled down. Temperature plays a role in ring dynamics as well. Ring particles are heated by sunlight and cooled by radiating infrared energy into space. The equilibrium temperature depends on the particle's size and composition. Larger particles have more thermal inertia and cool more slowly, while smaller particles respond quickly to changes in sunlight. These temperature variations affect how particles stick together when they collide, influencing whether the ring evolves toward larger clumps or maintains a population of smaller particles. The composition of ring particles varies widely between different planets and even within a single ring system. Saturn's rings are predominantly water ice, giving them their high reflectivity and bright appearance. The ice is remarkably pure, though there are trace amounts of rocky material and organic compounds that give some regions a slightly reddish or brownish tint. Uranus's rings, by contrast, are much darker, composed of material that reflects only a few % of the light that hits it. This dark material might be radiation-processed organic compounds, similar to the dark material found on some asteroids and comets. The age of ring systems is a matter of ongoing research and debate. Some rings might be primordial, dating back to the formation of the solar system itself 4.6 billion years ago. These would be rings made from material that was present in the disk of gas and dust from which the planets formed. Material that never coalesced into moons because it was inside the Roche limit. Other rings are clearly much younger, formed by relatively recent collisions or tidal disruptions. Saturn's rings, despite their prominence, might be surprisingly young. Several lines of evidence suggest they could be only a few 100 million years old. They're very bright and icy, lacking the darkening that would come from billions of years of meteorite bombardment. The amount of dust falling into Saturn's atmosphere from the rings suggests they're being depleted at a rate that couldn't be sustained over billions of years. If Saturn's rings are indeed young, it means we're living at a special time in the solar system's history, able to witness these magnificent structures during a brief window of their existence. Rings are not permanent features. They evolve over time, gradually spreading outward or inward, losing material to the planet's atmosphere or to moons, being disrupted by resonances or replenished by new collisions. Some ring systems might last for the lifetime of the solar system, while others might come and go over much shorter timescales. The rings we see today are snapshots in an ongoing process of creation, evolution, and eventual destruction. Even Earth might have had rings at some point in its distant past. Some researchers have suggested that a large impact that created debris in orbit could have temporarily given Earth a ring system that persisted for millions of years before the material either fell back to Earth or coalesced to form the Moon. While speculative, this idea reminds us that ring systems are dynamic features that can appear and disappear throughout a planet's history. The physics governing ring formation operates not just in our solar system, but around planets orbiting other stars as well. Exoplanets with large moon systems or recent collisions might sport ring systems, though detecting such rings at interstellar distances remains incredibly challenging with current technology. The same fundamental processes, tidal disruption, collisions, gravitational interactions, would operate universally, creating rings around any planet where conditions permit, adding layers of complexity and beauty to planetary systems throughout the galaxy. How evolution would work on other worlds. Evolution is not a theory specific to Earth. It is a fundamental principle that must operate wherever life exists, as inevitable as gravity or thermodynamics. The basic mechanism is elegantly simple. Organisms that are better suited to their environment tend to survive and reproduce more successfully than those less well suited, passing their advantageous traits to offspring. Over countless generations, this process of natural selection shapes organisms to fit their environments with remarkable precision. Charles Darwin recognized this principle in the 19th century by studying finches on the Galapagos Islands and countless other organisms, but the principle extends far beyond Earth. On any world where life emerges, evolution would be the engine driving biological diversity and adaptation, though the specific outcomes would be shaped by each world's unique conditions. The fundamental requirements for evolution are remarkably minimal. Life must be able to reproduce, creating offspring. There must be variation among individuals. No two organisms are exactly alike. Some of this variation must be heritable, passed from parents to offspring, and there must be differential survival and reproduction. Some variants survive and reproduce more successfully than others. These conditions create evolution automatically, inevitably, as surely as releasing a ball on a slope causes it to roll downhill. Any replicating system with heritable variation and selection will evolve, whether it's based on DNA, some other information storage molecule, or even non-biological replicating systems. On Earth, DNA serves as the information storage medium for nearly all life. The DNA molecule consists of two strands wrapped around each other in a double helix, with each strand composed of a sugar phosphate backbone and a sequence of 4 bases: adenine, thymine, guanine, and cytosine. The sequence of these bases encodes genetic information, and this information is copied when cells divide, passed to offspring when organisms reproduce. Mutations, random changes in the DNA sequence caused by copying errors, radiation, chemical damage, or other factors, create the variation upon which natural selection acts. But DNA is not the only possible genetic molecule. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information and be copied, yet use different sugars or even different backbone structures than natural DNA and RNA. These artificial genetic molecules demonstrate that information storage and heredity don't require DNA specifically. An alien organism might use a completely different molecule to store genetic information, perhaps based on different chemistry more suited to its world's conditions. A very cold world might favor genetic molecules that are stable and flexible at low temperatures. A very hot world might favor molecules that resist heat degradation. The specific molecule doesn't matter. What matters is that it can store information, be copied with reasonable but imperfect fidelity, and allow variation to arise. The timescales of evolution would differ dramatically on different worlds. On Earth, bacterial generations might span minutes to hours, allowing rapid evolution. The bacteria that cause diseases evolve antibiotic resistance within years or decades as antibiotics create selection pressure, favoring resistant strains. In contrast, large organisms with long generation times evolve more slowly. Elephants with generation times of decades evolve far more slowly than bacteria. On an alien world where organisms have extremely long lifespans, perhaps living for thousands of years, evolution would proceed at a glacial pace from a human perspective, with significant changes taking millions or billions of years. Conversely, on a world where organisms reproduce very rapidly, evolution might proceed at dizzying speeds. If alien microorganisms reproduced every few minutes, like some Earth bacteria, they could evolve through thousands of generations while we watched. Such organisms might adapt to new conditions, almost in real time, developing resistance to threats or exploiting new resources faster than slower evolving species could respond. The environment determines what traits are advantageous. On Earth, giraffes evolved long necks because reaching high branches provided access to food that shorter animals couldn't exploit. Cheetahs evolved extreme speed to catch fast prey. Cacti evolved to store water and reduce surface area in desert environments. Each adaptation reflects the specific challenges and opportunities of the organism's environment. On alien worlds, different environments would favor different adaptations. On a high-gravity planet, evolution would favor short, stocky body plans with strong skeletons and powerful muscles to support body weight against stronger gravitational pull. Tall, slender organisms would be at a disadvantage because the structural demands of supporting height would be too great. Flying organisms might be rare or absent because overcoming gravity to achieve flight would require enormous energy expenditure. Over millions of generations, organisms would become increasingly adapted to moving efficiently under high gravity, perhaps developing 4 legs or even 6 or 8 for stability, with low centers of gravity and massive muscular systems. On a low-gravity world, the opposite pressures would apply. Organisms could afford to be tall and slender because less structural support is needed. flight might be easy, favoring the evolution of wings and aerial lifestyles. Animals might leap enormous distances because the energy required to overcome gravity would be minimal. Over time, organisms might evolve increasingly delicate structures, abandoning the heavy skeletons and dense muscles necessary on higher gravity worlds in favor of lighter, more energy-efficient body plans. Atmospheric composition would profoundly influence evolution. On Earth, the transition from an oxygen-poor to an oxygen-rich atmosphere about 2.5 billion years ago, the Great Oxidation Event, was catastrophic for organisms adapted to the old atmosphere. Oxygen was toxic to them, and they retreated to oxygen-free refuges or went extinct. But for organisms that could tolerate or use oxygen, this chemical change created opportunities. Oxygen metabolism releases far more energy than anaerobic metabolism, enabling the evolution of larger, more active, more complex organisms. The size of organisms on Earth is ultimately limited by how efficiently they can deliver oxygen to their cells. On a world that never develops an oxygen-rich atmosphere, organisms might remain permanently small and metabolically limited. Without the high energy yield of oxygen metabolism, active lifestyles like those of birds, mammals, or even fish might be impossible. Life might consist entirely of small, slowly moving organisms eking out existence on the limited energy available from anaerobic metabolism. Or evolution might discover entirely different high-energy metabolic pathways based on different oxidizing agents, perhaps sulfur compounds, chlorine, or substances we haven't considered. The availability of water determines many evolutionary paths. On Earth, life originated in water, and even terrestrial organisms remain fundamentally aquatic. Our cells are filled with water, and we constantly need to replenish water lost to evaporation and excretion. On a water-rich world with extensive oceans, evolution might produce countless aquatic species, but might never develop terrestrial life if there's no advantage to leaving water. On a dry world with limited water, evolution would favor organisms that conserve water ruthlessly, perhaps evolving impermeable skins, efficient kidneys, metabolic water production, or even the ability to extract water from food or from humidity in air. Predation creates powerful selection pressures that drive evolutionary arms races. Prey evolve defenses, armor, toxins, speed, camouflage, while predators evolve counter-adaptations to overcome those defenses. Stronger jaws, detoxification mechanisms, greater speed, better sensory systems. This coevolution produces increasingly sophisticated organisms on both sides. On Earth, the evolution of predators coincides with the evolution of many complex features: eyes to detect prey, brains to process sensory information, and coordinate hunting strategies, complex behaviors for stalking and capturing prey. On alien worlds, predation would likely emerge wherever life becomes sufficiently complex, driving similar evolutionary arms races, but the specific adaptations would reflect the alien environment. On a world with dense fog or darkness, evolution might favor chemical or acoustic sensing over vision. On a world with three-dimensional environments, like open water or thick forests, predators might evolve better spatial perception and three-dimensional maneuverability. On a world where prey can burrow or fly, predators would evolve means to follow them into those refuges. Sexual selection, where organisms choose mates based on specific traits, creates another evolutionary force. On Earth, peacocks evolved elaborate tails, not because those tails help survival, but because peahens prefer males with impressive tails. This sexual selection can drive the evolution of traits that actually reduce survival, but increase reproductive success. On alien worlds, whatever traits the choosing sex prefers would be amplified through generations, potentially creating wildly extravagant features that serve no purpose beyond attracting mates. Convergent evolution, where unrelated organisms independently evolve similar solutions to similar problems, demonstrates that certain designs work well for certain challenges. Eyes evolved independently many times on Earth because detecting light provides such valuable information that natural selection repeatedly favoured organisms with improved light-sensing abilities. Wings evolved independently in insects, birds, bats, and pterosaurs because flight provides such significant advantages that multiple lineages evolved aerial capabilities. On alien worlds, convergent evolution would operate similarly. Any organism that needs to move quickly through water would likely evolve a streamlined body shape because physics dictates that this shape minimizes drag. Any organism that needs to see would likely evolve some structure that focuses light onto photosensitive cells, though the specific implementation might differ. Any organism that needs to manipulate objects would likely evolve some form of grasping appendages. The specific details would vary. Alien hands might have 3 fingers or 7, might be at the end of tentacles or rigid arms, might use suction or hooks instead of friction, but the basic function of grasping would emerge wherever it provides advantage. However, historical contingency, the accidents of evolutionary history, also plays a crucial role. Vertebrates on Earth have 4 limbs because that's what the early fish that first crawled onto land happened to have. There's nothing inevitable about the number 4. If a 6-limbed fish had been the first successful land colonizer, terrestrial vertebrates might all have 6 limbs today. On alien worlds, similar historical accidents would lock in features that become constraints on all future evolution. An early successful body plan might dominate an entire planet's evolutionary tree, with all descendants constrained by that ancestral architecture. Mass extinctions reset evolutionary trajectories. On Earth, the asteroid impact 66 million years ago that killed the non-avian dinosaurs allowed mammals, previously small nocturnal creatures, to diversify into the enormous variety we see today. Without that extinction, mammals might have remained small and marginal while dinosaurs continued dominating. On alien worlds, whatever catastrophes occur, asteroid impacts, volcanic eruptions, climate changes, nearby supernova, would similarly reset evolution, wiping out dominant groups and allowing previously marginal organisms to radiate into newly available ecological roles. The speed of environmental change influences evolutionary dynamics. Rapidly changing environments favour organisms with short generation times and high mutation rates that can adapt quickly. Stable environments favour organisms optimised for efficiency in unchanging conditions. An alien world with a highly variable climate, perhaps due to an eccentric orbit or an unstable star, would see evolution favouring adaptable generalists. A world with stable conditions for billions of years might produce highly specialised organisms, exquisitely adapted to narrow niches, but unable to cope with change. Intelligence itself is an evolutionary adaptation that emerged on Earth because it provided survival and reproductive advantages. Brains require enormous energy. Human brains consume about 20% of our total energy, despite being only 2% of body mass. This high cost means intelligence only evolves when its benefits outweigh its costs. On Earth, intelligence apparently provided sufficient advantage through tool use, social cooperation, and problem solving to justify the expense. On alien worlds, whether intelligence evolves depends on whether similar advantages exist. Some environments might favour intelligence more strongly than Earth did. A highly variable environment where adaptability is crucial might select strongly for intelligence and behavioural flexibility. A world where organisms compete primarily through social manipulation rather than physical prowess might favour intelligence. Conversely, some worlds might never produce intelligence because simpler solutions always work well enough. If food is always abundant and predators are absent, the energy costs of maintaining a large brain might never be justified. How evolution would work on other worlds follows the same fundamental principles that operate on Earth: variation, heredity, and selection, but expresses those principles through the unique circumstances of each world. A high-gravity planet would sculpt short, powerful organisms. A dark world might favour chemical sensing over vision. A frigid world might produce organisms with anti-freeze biochemistry and slow metabolisms. Each world would develop its own evolutionary history, branching from simple origins into complexity through billions of years of selection, extinction, radiation, and adaptation, creating ecosystems and organisms as unique as fingerprints, yet fundamentally related through the universal principles of evolution that must operate wherever life exists, proving that while life-specific forms might be infinitely varied across the cosmos, the process that shapes life, evolution through natural selection, remains constant, an inevitable consequence of imperfect replication and limited resources operating across deep time on any world that hosts living things. How aliens could breathe. Different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic: hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure, and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, this zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath the Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice, material that spacecraft have flown through and analyzed. The presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favourable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbor life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harboring biospheres in their hidden oceans. Binary star systems, where two stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from two suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets, and the basic ingredients for life, elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our Sun, the temperature at the center reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain. Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected, the antimatter counterpart of an electron. A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light, and energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has two protons and one neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, two helium-3 nuclei collide and fuse, forming ordinary helium-4, which has two protons and two neutrons, and releasing two protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into one helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy, according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface, to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity. Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our Sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the Sun is actually a fairly average, middle-sized star. Some massive stars output 1,000,000 times more energy than the Sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the Sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the Sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars. How extraterrestrial plants could photosynthesize. Photosynthesis, the process by which plants, algae, and certain bacteria capture light energy and convert it into chemical energy, powers most of Earth's ecosystems. Green plants absorb sunlight, split water molecules, combine carbon dioxide from the air with hydrogen from the water, and produce sugars while releasing oxygen as a byproduct. This process transformed Earth's atmosphere from oxygen-poor to oxygen-rich over billions of years, enabling the evolution of complex animal life. Photosynthesis seems so central to life that we naturally wonder whether alien plants on distant worlds would photosynthesize in similar ways. The answer is nuanced. While capturing energy from starlight would likely be advantageous for life on any illuminated world, the specific chemistry and mechanisms of alien photosynthesis would differ dramatically depending on the star's properties, atmospheric composition, available pigments, and evolutionary history of each world. On Earth, photosynthesis centers on chlorophyll, a complex molecule containing magnesium at its center, surrounded by a ring structure that absorbs light strongly in the red and blue portions of the spectrum while reflecting green light, which is why plants appear green. Chlorophyll's absorption spectrum is not random but reflects the properties of sunlight. Our Sun is a yellow dwarf star with a surface temperature around 6,000 degrees Celsius, emitting light most strongly in the visible portion of the spectrum that our eyes evolved to see, with peak emission in the green-yellow range. Plants evolved pigments that absorb the abundant wavelengths while reflecting the less useful portions. But most stars in the galaxy are red dwarfs, cooler, smaller stars with surface temperatures around 3,000 degrees that emit most of their light in the red and infrared portions of the spectrum. A planet orbiting in the habitable zone of a red dwarf would receive much less visible light and far more infrared radiation than Earth receives from our Sun. Photosynthetic organisms on such a world would need to adapt to this shifted spectrum, likely evolving pigments that absorb infrared light rather than visible light. Capturing infrared photons presents challenges because each infrared photon carries less energy than a visible light photon. On Earth, Chlorophyll uses two photons, absorbed at different stages of photosynthesis, to extract enough energy to split water molecules, which requires significant energy input. With lower energy infrared photons, alien photosynthesis might need to capture 3 or even 4 photons per reaction to gather sufficient energy, making the process less efficient. However, red dwarf stars are extremely common and extremely long-lived, shining for trillions of years compared to the Sun's 10 billion year lifespan. So even if photosynthesis is less efficient under red dwarf light, organisms would have enormous amounts of time to evolve and adapt. The pigments that absorb infrared light would likely appear black or very dark to human eyes because they would absorb nearly all visible light in addition to infrared. A forest on a red dwarf planet might be covered in black vegetation, maximizing absorption of every available photon from the dim red star. This is the opposite of Earth's green plants, which reject green light as insufficiently useful. On a planet where photons are precious, wasting any light would be disadvantageous, so evolution would favor organisms that capture everything. Conversely, planets orbiting hot, bright blue or white stars would receive intense ultraviolet radiation, along with visible and infrared light. Ultraviolet photons carry high energy, potentially too much energy, as UV light damages DNA and proteins. Photosynthetic organisms on such worlds might evolve pigments that specifically avoid ultraviolet absorption, reflecting or dissipating UV light while capturing only visible wavelengths. Or they might evolve protective mechanisms, UV-absorbing compounds in outer cell layers, extremely efficient DNA repair systems, or pigments that can safely handle high-energy photons by converting excess energy into heat or fluorescence. The color of alien plants would thus depend on their star's spectrum. Under orange K-type stars, plants might be red or orange, reflecting the most common light while absorbing other wavelengths. Under blue stars, plants might be yellow or orange. The specific colors would depend not just on what light is available, but also on what pigments evolution happens to discover and what combination of wavelengths provides optimal energy capture. Multiple pigments working together might be advantageous. On Earth, plants contain several pigments beyond chlorophyll, carotenoids, that absorb blue and green light, appearing yellow, orange, or red, and other accessory pigments that expand the range of useful wavelengths. These accessory pigments capture light that chlorophyll misses and transfer the energy to chlorophyll for use in photosynthesis. Alien plants might evolve even more diverse pigment systems, with perhaps 5 or 10 different pigments, each specialized for different wavelength ranges, collectively capturing a broader spectrum than Earth's photosynthetic organisms manage. The electron transport chains that actually convert light energy into chemical energy might use different chemistry than Earth's photosynthesis. On Earth, photosynthesis splits water molecules to extract electrons, releasing oxygen gas as waste. But water splitting is energetically demanding. It requires significant light energy input. An alien photosynthesis might use different electron donors that are easier to oxidize than water. Hydrogen sulfide, for instance, is easier to split than water and was likely used by early photosynthetic bacteria on Earth before oxygen-producing photosynthesis evolved. A planet with abundant hydrogen sulfide might develop photosynthetic life that remains at this stage indefinitely, producing elemental sulfur rather than oxygen as waste. Ion compounds, organic molecules, or even molecular hydrogen could serve as electron donors in alternative photosynthetic pathways. Each would produce different waste products. Ion photosynthesis might precipitate iron oxides. Organic-based photosynthesis might produce various carbon compounds, and hydrogen-based photosynthesis might produce protons that combine with other elements. None of these would generate an oxygen-rich atmosphere, demonstrating that photosynthesis doesn't necessarily equal oxygen production. The carbon source might also vary, Earth plants use carbon dioxide from the atmosphere as their carbon source, but CO2 concentrations vary dramatically across different worlds. Venus has a thick CO2 atmosphere, but is far too hot for life as we know it. Mars has thin atmosphere that's mostly CO2, but overall, CO2 availability is low due to the low pressure. A planet with very low atmospheric CO2 might require photosynthetic organisms that can concentrate and capture CO2 extremely efficiently, perhaps with specialized structures or enzymes far more effective than Earth's plants possess. Alternatively, alien photosynthesis might use carbon sources other than CO2. Carbon monoxide, methane, or even dissolved bicarbonate in water could provide carbon for building organic molecules. Each source would require different enzymatic machinery and would produce different end products. Methane-based photosynthesis might produce more complex hydrocarbons, essentially reversing the process that creates methane on Earth. ICO-based photosynthesis might build organic molecules through different chemical pathways than CO2-based photosynthesis uses. The physical structure of alien photosynthetic organisms might differ radically from Earth's plants. Trees evolved on land where structural support is needed to compete for sunlight, growing tall to shade competitors. But on a planet with perpetual dense cloud cover, blocking direct sunlight and providing only diffuse illumination, there would be no advantage to height. All locations would receive similar light levels. Plants might remain low-growing, perhaps forming dense mats rather than tall structures. On a planet with a very thin atmosphere, providing minimal structural support, perhaps Mars if it ever hosts photosynthetic life, organisms might need to be extremely sturdy and low-profile to withstand wind without atmospheric cushioning. Or on a high-gravity world, the structural challenges of growing tall might be prohibitive, keeping photosynthetic organisms close to the ground in spreading horizontal forms rather than vertical trees. Aquatic photosynthesis might dominate on ocean worlds. Earth's oceans contain vast amounts of photosynthetic organisms, phytoplankton, algae, and photosynthetic bacteria that drift or swim in the water column, capturing sunlight in the upper illuminated layers. On a world covered entirely by ocean, with no dry land, all photosynthesis would necessarily be aquatic. These organisms might evolve greater efficiency at capturing dim light filtered through water, or might develop gas-filled structures to regulate their depth, staying in the optimal light zone. Deep-sea photosynthesis might even be possible using not sunlight, but the faint light produced by hydrothermal vents or bioluminescence. On Earth, some photosynthetic bacteria near deep-sea vents use the faint thermal radiation from the hot vent fluids. This produces very little energy, but it demonstrates that photosynthesis isn't absolutely dependent on sunlight. An alien world with extensive hydrothermal activity might develop photosynthetic life that uses volcanic light, living in eternal darkness sustained by geothermal rather than solar energy. Bioluminescence-powered photosynthesis could create bizarre ecological cycles where organisms generate light through chemical reactions, other organisms use that light for photosynthesis, and the products of photosynthesis support the light-generating organisms. This would be less efficient than using a star's light directly. But on a rogue planet drifting through interstellar space with no star, such a system might be the only way photosynthesis could exist at all. The efficiency of photosynthesis varies greatly on Earth, with most plants converting only 1 to 2% of incoming light energy into chemical energy stored in sugars. This low efficiency reflects various constraints and trade-offs in the photosynthetic machinery. Alien photosynthesis might achieve higher efficiency through different molecular mechanisms, different pigment arrangements, or different metabolic pathways. Alternatively, on worlds where light is extremely dim, even 1 or 2% efficiency might be insufficient, driving evolution toward photosynthetic systems that capture and convert light more effectively, perhaps achieving 5 or 10% efficiency through molecular innovations not present on Earth. Timescales of photosynthesis might differ on other worlds. Earth's photosynthesis operates on timescales of milliseconds to seconds for individual reactions, constrained by the speed of enzyme reactions at Earth's temperatures. On a very cold world, reaction rates would be much slower. Photosynthesis might take minutes or hours for reactions that complete in seconds on Earth. This would mean slower growth rates and organisms that live life in slow motion from our perspective. On a hot world, reactions might proceed faster, allowing rapid photosynthesis and potentially faster growth, though this would also require dealing with the instability of biological molecules at high temperatures. The evolution of photosynthesis on Earth took hundreds of millions of years, with simpler forms appearing first and the complex, oxygen-producing photosynthesis we see in plants evolving later. On alien worlds, the evolutionary trajectory might differ. Perhaps photosynthesis evolves quickly, becoming established within the first billion years of life's appearance. Or perhaps it never evolves at all, with life remaining dependent on chemical energy from geological processes rather than light energy. Photosynthesis, while extremely useful, is not inevitable. It requires specific evolutionary innovations, including light-sensitive pigments, electron transport machinery, and carbon-fixing enzymes. A planet might have abundant life that never discovers photosynthesis, remaining microbial and chemosynthetic indefinitely. The seasonal variations on alien worlds would influence photosynthetic strategies. A planet with extreme axial tilt might experience dramatic seasonal variations in light availability, requiring photosynthetic organisms to either hibernate during dark seasons, store energy during bright seasons, or maintain alternative metabolic modes that don't require light. A tidally locked planet with one side permanently facing its star would have a permanent light side and permanent dark side, with photosynthesis possible only on the lit hemisphere or in the twilight zone between light and dark. The atmospheric chemistry would affect what wavelengths reach the surface. Earth's ozone layer absorbs harmful ultraviolet light, preventing it from reaching the surface. A planet without an ozone layer would expose surface organisms to intense UV, requiring either UV protective mechanisms or restriction of photosynthetic life to water, which naturally blocks UV. A planet with a different atmospheric composition, perhaps with sulfur compounds, nitrogen oxides, or exotic hazes, would filter light differently, creating different wavelengths available at the surface, and thus different optimal pigments for photosynthesis. How extraterrestrial plants could photosynthesize encompasses a vast range of possibilities shaped by stellar spectra, atmospheric filtering, available chemistry, and evolutionary contingency. From black plants absorbing every photon under dim red suns to colourful organisms reflecting abundant high-energy light under bright blue stars. From water-splitting oxygen producers to hydrogen sulfide users releasing sulfur. From rapid tropical growth to slow cold world metabolism, alien photosynthesis would adapt to each world's unique conditions while performing the same basic function, capturing light energy and converting it into chemical energy that powers ecosystems, potentially creating oxygen-rich atmospheres, modifying planetary chemistry in detectable ways, and revealing through their presence that life has discovered on distant worlds what it discovered on Earth. That starlight, properly harnessed through molecular machinery, shaped by billions of years of evolution, can power the chemical reactions that sustain living things, turning distant stars into energy sources for biology across the galaxy. How the moon pulls on Earth's oceans. Twice each day, the ocean rises up beaches and coastlines around the world, then retreats back toward the sea. This rhythmic rise and fall of the tides has shaped human civilization for thousands of years. governing when ships could enter harbours, when fishermen could gather shellfish from tidal pools, and when coastal communities needed to prepare for high water. The connection between these tides and the moon was recognised in ancient times, but understanding exactly how the moon creates tides requires thinking carefully about gravity, how it varies with distance, and how Earth's ocean responds to forces that stretch and squeeze it in complex ways. The fundamental cause of tides is gravity, but not gravity in the simple sense of the moon pulling water toward itself. If that were the entire story, we would see one bulge of water on the side of Earth facing the moon, and that would be the end of it. Instead, we observe two tidal bulges, one on the side facing the moon and another on the opposite side of Earth. This puzzling fact confused natural philosophers for centuries, until Isaac Newton, in his Principia Mathematica, published in 1687, provided the correct explanation using his law of universal gravitation and his laws of motion. The key insight is that the moon's gravity pulls on every part of Earth, but it pulls with different strengths depending on distance. The side of Earth closest to the moon experiences stronger gravitational attraction than Earth's centre, which in turn experiences stronger attraction than the far side. This difference in gravitational force across Earth's diameter creates what are called tidal forces, forces that try to stretch Earth along the line, connecting it to the moon, while simultaneously squeezing it perpendicular to that line. Imagine Earth's structure for a moment. The solid rock of Earth's crust and mantle resists deformation quite strongly. While tidal forces do deform the solid Earth slightly, raising and lowering the ground by about a foot, the effect is not dramatic because rock is stiff and strong. The oceans, however, are fluid. They can flow freely in response to forces, and they respond readily to the tidal forces that the solid Earth largely resists. Consider a point on Earth's surface directly beneath the moon. The water at this location is about 4,000 miles closer to the moon than Earth's centre. The moon's gravitational pull weakens with distance according to an inverse square law. Double the distance and the force becomes 1/4 as strong. This means the ocean on the near side experiences a gravitational pull toward the moon that's about 7% stronger than the pull experienced by Earth's centre. This differential force pulls the ocean away from Earth's centre, creating a bulge of water on the moon-facing side. Now consider the opposite side of Earth, the point farthest from the moon. Here the ocean is about 4,000 miles farther from the moon than Earth's centre. The gravitational pull from the moon at this location is about 7% weaker than at Earth's centre. Earth's centre is being pulled toward the moon more strongly than the water on the far side, effectively pulling Earth away from the water and leaving the water behind. The result is another bulge on the side opposite the moon. This creates the characteristic two-bulge pattern. If you could freeze time and look at Earth from space, you would see the oceans slightly elongated along the Earth-Moon line, with high water on both the near and far sides and low water at the points 90 degrees away from the moon. As Earth rotates beneath these bulges, any given point on Earth's surface passes through two high tides and two low tides each day, though not exactly every 12 hours, because the moon is also moving in its orbit, shifting the position of the bulges over time. The height of these tidal bulges would be quite modest if they responded only to the moon's gravitational pull, perhaps a foot or two in the open ocean. But the actual tides we observe at coastlines can be dozens of feet high. This amplification occurs because of the way ocean basins are shaped and because of resonance effects as water sloshes back and forth in confined spaces. The Bay of Fundy in Canada experiences the world's highest tides, sometimes exceeding 50 feet, because the bay's shape and size create a natural resonance that amplifies the tidal forcing from the moon and sun. The sun also creates tides on Earth, though they're smaller than lunar tides despite the sun's vastly greater mass. The reason is distance. The sun is about 400 times farther from Earth than the moon, and tidal forces depend not just on mass, but on how much the gravitational pull varies across Earth's diameter. The Sun's great distance means its gravitational pull varies less across Earth than the Moon's does, making solar tides about 46% as strong as lunar tides, a ratio that Pierre-Simon Laplace calculated in detail in his comprehensive work on celestial mechanics in the late 1700s. The interaction between solar and lunar tides creates the familiar spring and neap tide cycle. When the Moon and Sun align, either on the same side of Earth during a new moon or on opposite sides during a full moon, their tidal effects add together, creating spring tides with especially high tides and especially low tides. The name has nothing to do with the season, but comes from the idea that the tides spring forth. When the Moon and Sun are at right angles as seen from Earth during first and third quarter moons, their tidal effects partially cancel, creating neap tides with smaller tidal ranges. This 2-week cycle of spring and neap tides is predictable and was well understood by ancient mariners, though they lacked Newton's gravitational explanation for why it occurred. The timing of tides is not as simple as one might expect. If you observe the tides at any coastal location, you'll notice that high tide doesn't occur exactly when the Moon is overhead or exactly when it's on the opposite side of Earth. There's typically a delay of several hours called the tidal lag. This occurs because the ocean cannot respond instantaneously to the changing tidal forces. Water has inertia, it takes time to accelerate and decelerate, and friction between the moving water and the ocean floor dissipates energy, creating phase lags between the tidal forces and the ocean's response. These friction effects have profound long-term consequences. As tidal bulges try to follow the Moon, but are dragged forward slightly by Earth's rotation, they create a gravitational pull on the Moon that's not perfectly aligned with the Earth-Moon line. This misaligned pull acts to accelerate the Moon in its orbit, gradually increasing its orbital energy and causing it to move away from Earth. Precise laser ranging measurements using reflectors left on the Moon by Apollo astronauts have confirmed that the Moon is receding from Earth at about 1.5 inches per year. This recession cannot continue indefinitely at the current rate. As the Moon moves farther away, tidal effects weaken, slowing the recession. But over the 4.5 billion years since the Moon formed, likely from debris created when a Mars-sized object collided with the young Earth, the Moon has moved substantially farther from Earth. Early in Earth's history, when the Moon was much closer, perhaps only 15,000 miles away compared to today's 240,000 miles, tidal forces were enormously stronger. Tides might have been hundreds of feet high, and the Moon would have appeared many times larger in the sky, looming over the horizon like an enormous sphere dominating the heavens. The energy dissipated by tidal friction doesn't just affect the Moon's orbit, it also affects Earth's rotation. The gravitational drag from the tidal bulges acts to slow Earth's rotation gradually. Each century, Earth's day lengthens by about 1.7 milliseconds. This seems negligible, but over geological time, it accumulates. Fossil evidence from ancient corals, which show daily growth bands much like tree rings, indicates that 400 million years ago, Earth's day was only about 22 hours long, and a year contained about 400 days. The Moon was closer, Earth rotated faster, and tides were stronger. This tidal interaction between Earth and the Moon is an example of tidal locking in progress. The Moon is already tidally locked to Earth, always showing the same face toward Earth because tidal forces from Earth have synchronized the Moon's rotation period with its orbital period. Earth is gradually becoming tidally locked to the Moon as well, though this process will take tens of billions of years to complete, longer than the remaining lifetime of the Sun. If it could be completed eventually, Earth would always show the same face to the Moon, and the Moon would hang stationary in the sky over one hemisphere, never visible from the other. Other bodies in the solar system experience even more extreme tidal effects. Jupiter's moon, Io, the most volcanically active body in the solar system, is heated internally by tidal flexing. As Io orbits Jupiter in an elliptical path, the tidal forces it experiences vary in strength, squeezing and stretching the moon's interior. This constant kneading generates tremendous heat through friction, keeping Io's interior molten and driving its spectacular volcanic eruptions. This process, predicted by Stanton Peele and colleagues just before the Voyager spacecraft discovered Io's volcanism in 1979, is called tidal heating. Saturn's moon Enceladus experiences similar tidal heating, though less extreme than Io. The heat from tidal flexing keeps a subsurface ocean liquid beneath Enceladus's icy crust, and tidal stresses crack the ice at the South Pole, allowing geysers of water to erupt into space. Europa, another moon of Jupiter, likely has its subsurface ocean maintained by tidal heating as well, making it one of the most promising places to search for life beyond Earth. Tidal forces can also be destructive. Every large body creates a tidal limit, called the Roche limit, after Edouard Roche, who calculated it in 1848, inside which tidal forces exceed the self-gravity holding a satellite together. A moon that wanders inside the Roche limit will be torn apart by tidal forces, pulled into fragments that spread into a ring around the planet. Saturn's magnificent ring system may have originated this way, from a moon that either formed inside the Roche limit or migrated inward and was disrupted. Tidal forces operate throughout the universe. Binary stars experience tides that can transfer mass from one star to its companion. Black holes create tidal forces so extreme that they can tear apart stars that pass too close, creating spectacular tidal disruption events. Galaxies passing near each other experience tidal forces that stretch them into long streams of stars, creating the tidal tails visible in many interacting galaxies. The same physics that causes ocean tides on Earth, the differential pull of gravity across an extended object, operates on scales from moons and planets to stars and galaxies. The tides we observe at the beach are the local manifestation of a cosmic dance between Earth and Moon, a gravitational interaction that has been occurring since the Moon formed and will continue for billions of years into the future. Every incoming wave, every tide pool exposed at low tide, every ship waiting for high water to enter harbour is part of this larger story of how gravity shapes the motion of celestial bodies, and how the Moon, our constant companion in the night sky, continues to sculpt the behaviour of Earth's oceans through the subtle but inexorable pull of tidal forces.